Reflections and guide reflections and glide reflections. So this is going to be a reflection. This is our line of reflection. That's what you need for a reflection, a line of reflection, what's going to act like a mirror, somewhat like a mirror. Here's our pre-image. So we're going to get a copy on the other side of the line of reflection, the same distance away. So you take each point, each of the vertices, and one by one, you put them on the other side, but the same distance away it was on the other side before you reflected. So here's the pre-image, here's the image. They should be the same distance away from the line of reflection. And not only that, you should be able to join these 2 points with a line segment that's perpendicular to the surface. It always has to be perpendicular to the surface, the line segment that joins the pre-image and the image of a reflection. So after you do all this, this is the image you end up with. Here's another practice problem. Line M was going to be the line of reflection. And this line that you see here is going to be the line we're going to reflect. Notice that unlike like a mirror, you don't go through the mirror in real life, but right here you could go through the line of reflection. So the line of reflection is not a mirror, but it's like a mirror. What you need are 2 points to draw the next line. 2 points draws you a unique line. So what you do is pick a point. So I'm going to pick this one. And it should be, this is the pre-image, the before. And I'm going to reflect it going that direction. So it should be the same distance away on the other side. And a line segment perpendicular joins them both, the pre-image and the image. This one's an easy one to pick because this one's not going to move. When you actually intersect the line of reflection, the pre-image and the image are the same. So now we have these 2 points. You join them, and this gives you the image line. A glide reflection involves two steps. A glide followed by a reflection. So we're going to translate slide, the figure, and then reflect it. So here is the pre-image triangle. Here's our slide arrow. It tells us how much to slide it and in which direction. So take each one of these points and slide it this amount. This is its new location. A prime, B prime, C prime. So it's an image. But we don't stop there. We did the translation. Now we're going to reflect. We're going to let this be the line of reflection. So take each one of these points and reflect it. Reflect it, reflect it. This is the reflection part. This is the image you keep, the last one. Notice it has double primes. The one that has most primes is the one that's the latest. Question, would we have gotten the same result if we would have reflected and then glided? The answer is yes. The order doesn't affect the final result. Dilations do affect the size. They either reduce the size or magnify the size. What do you need for a dilation? A center of dilation and a scale factor. Notice the word factor implies there will be a multiplication. Here's an example. We're going to use O as a center of dilation. So the center of dilation, points either move towards it or away from it. But how much? Well, the scale factor gives us that information. So the original length, we'll let that be 1. This is 1. The original length is 1. Since we're going to use a scale factor of 2/3, we divide it in 2/3. And 2 of the thirds of the original length is where the pre-image will be going. So it was here, and it's moving to this place because this is 2/3 of the original distance. So the original distance will be 1. 1 times 2/3, 2/3. This is our after look, the P prime, the image. Here we have a polygon. This is a quadrilateral. And what you do is you do exactly what we did in the previous slide. You take each one of these points, tie it up to the center of dilation, and that's the original distance. We're going to use a scale factor of 2/3, so divide it in 2/3, And 2/3 of each of these distance would put each of these vertices in the 2/3 location. Notice this was the 1, and this is 2/3 of the distance. Same with the 8, 2/3 of its original distance, and so forth. This is the image. Let's summarize here the scale factor. If the scale factor is k, then if the k is greater than 1, expect the points to move away from the center of dilation. And if the k, the scale factor, is between 0 and 1, expect the points to move towards, closer to the center of dilation. More practice. Right here, they want us to identify the center of dilation and the scale factor. So identifying the center of dilation is like asking, towards or away from which point is the figure moving? Well, they told us in the problem that the little triangle is becoming the big one. So this point here, the one that we're calling point A, is the center of dilation. Since the little triangle is becoming the bigger triangle, then we ask, how do we know how big? The scale factor tells us. What number must I multiply the original lengths to get the final lengths? Well, you observe and count these little squares in the grid. The 3 became a 6, the 2 became a 4. That means I'm multiplying all the lengths times 2. So that will be my scale factor. Tessellations in a plane, a simpler way of saying that is tiling. When you tile the floor, you're tessellating the floor. To tessellate means that when you tile it, you shouldn't have any gaps or overlaps. But how do we know ahead of time whether the tessellation can be done? In other words, can be done with no gaps or overlaps. Here's a simple tessellation, like a floor. Observation, notice about each vertex, these angles go around it. So if you were to add these angles and they add up to 360, you could tile this surface without having gaps or overlaps. So the key is the sum should equal 360. The sum of the individual angles about the vertex for each vertex should add up to exactly 360 degrees. Tessellation with regular polygons. Regular means the sides are equal and the angles are equal. The number of polygons coming together at each vertex cannot be less than 3. In other words, when you're going to tile the surface, you need at least 3 tiles. You could have more than 3, but at least 3. So if you see these figures here, and just imagine tiling the surface with just these around, the 60, I should be able to add this angle and come up with a sum of 360. Same thing here. If you look at 108 and you say 360 divided by 108, you're not going to get an exact number. So even though this was a candidate, the only ones you could tile with regular polygons, the only regular polygons you could tile with a flat surface are the equilateral triangle, the square, and the regular hexagon.